announcements. So I assume folks who are registered for the course saw the email that it seems like everyone needs Friday, so welcome to Friday. And we'll just move the homework to that. That works better for everybody. And there will be a Public 3 coming soon. All right, and all the notes and the videos through last week are posted. We'll have the others posted soon. All right, so last time we were reviewing some of the very fundamentals about entanglement, one of the most important non-classical features. Some may argue you can argue not that, but you know, that's the key to everything, but in any event, it is certainly something. And in particular, we're focusing on the case where we're looking at a system that is so-called bipartite, okay? Has two parts, or as we sometimes call them, subsystems, or degrees of freedom. They're the quantum mechanical generalizations of when we think about the classical mechanical system with multiple degrees of freedom. Each degree of freedom we would think about as a subsystem, okay? The algebraic structure we talked about reminded ourselves about the tensor product structure for a bipartite system, where these represent two degrees of freedom that are distinguishable, okay? When we have indistinguishable particles, life becomes more complicated, and we don't have necessarily, it's not a natural tensor product structure, and the whole story about entanglement gets confused, and I think lots of people are confused about it. I should mention what it means for things to be distinguishable means, you know, for sure, if we have two subsystems that don't overlap in space anywhere, well, then they're distinguishable. The one that's in this place is what I'm calling A, and the one that's in that place is what I'm calling B. The fact that they might be two electrons, which are in principle fermions and indistinguishable, is irrelevant. It's completely irrelevant, because if the wave packets don't interact, for all intents and purposes, they're distinguishable. They only become, the aspects of indistinguishability only are important when they spatially overlap with one another. Then we have to worry about it. But if they don't, we don't, okay? Another important thing that people get confused about. All right, so we have these two subsystems. We can think about them as represented by each subsystem has some Hilbert space, which is a d-dimensional system A for subsystem A, subsystem B. They could both be infinity, or one could be infinity, the other one 2, or they can be whatever finite numbers we like. And we say that if we have a state of the system which is a tensor product of two pure states for the system, then we say this is a product state, and the measurement outcomes for whatever I measure on A or B are uncorrelated, okay? They're statistically independent outcomes. If I have a pure state that isn't a product state, then it's an entangled state, which means, amongst other things, that measurement outcomes are not statistically independent from one another. They're correlated, but they're correlated in a very special way. And to emphasize that fact, we were talking last time just of the most simple example. If we had a spin singlet state, two spin 1/2 particles, so we have each subsystem is a qubit, then this is an example of an entangled state. This measurement outcomes are correlated here, those measured outcomes, for example, if we measured in the sigma z basis for A and the sigma z basis for B, then we get these possibilities with 50% of the time. Either Alice will see up or down, and Bob will see the anti-correlated up and down, okay? Now that's also true for this state. This state will see exactly the same measurement statistics. And I like to emphasize one of my favorite experiments. This time, because Brandon is over here, Brandon gets to do the experiment with me, okay? Everyone sees nothing up my sleeve. I got a red cap and a pinkish cap. And you see, there's only one of each, right? Everyone close your eyes. Brandon, close your eyes. Open your hand. Close your hand. Okay. Open your eyes. Look at what's your chance? You're gonna get a pink or a blue? 50-50.
50-50.
Yeah. You open your, guess what I have?
Almost certainly the blue.
Exactly. Wow. You predicted what I had, and maybe you could have sent me a light signal and buzzed my phone, but you didn't. I know you didn't because we didn't plan ahead. So the fact that we have correlations and you can instantly predict what I am going to see is not a shocking thing. There was a pre-arranged correlation between those two colors, and that's described in some sense by this case where red and blue or red and pink or whatever we call it, blue and pink, were the two possibilities. This state we would not call entangled. This state is separable, even though it's not a product state. So the term separable is a stupid term that kind of became the standard. It really means not entangled. It's an unentangled state, but it is correlated. Okay? And one can define a state, a general state, is unentangled, also known as separable, if and only if rho can be written as a convex combination of product states. Okay, where these are classical probabilities. So they're greater than 0. They're real numbers, okay? So if I can write the joint state of the system as a statistical mixture of product states, I say we call that by definition an unentangled state, a separable state, okay? Now, this does not mean that that A and B are uncorrelated with one another. They would be uncorrelated if PAB was statistically independent and that was equal to the product of some probability on A and probability on B. Then that's a product state, and a product state is a uncorrelated state. But a state like this, we would say, is not entangled. Okay? And it's a complicated mess to know when states are unentangled or not. There are some tests we can do in some cases. If we got qubits, some of you may know about the positive partial transpose test and other tests, but generally speaking, it's kind of impossible to know. When we have a pure state of the overall system, then we can know a lot, and that's what we're going to talk about today. Okay. So one of the things we learned last time, or we reminded ourselves of last time, is that if the joint state of the system is pure, then the marginal states of the subsystems are pure only for product unentangled states. Otherwise, the marginals are mixed. So the degree increase of mixedness of marginals is in one-to-one corresponding with degree of entanglement if and only if the joint state is pure. Okay, and to remind you what I mean by the marginal, what we said is that if I had a joint state of the system, rho AB, then the marginal is the partial trace over the total. Okay, and similarly for subsystem B, as we discussed last time. So for the case of the singlet, if I ask what is the marginal of the what is the state of the system for spin A, doing the partial trace, we get this. Which is the identity. And similarly for B. Okay. Now that's also true for this state. So the fact that the marginal is mixed is not a signature that the joint state was entangled. I mean, when Brandon was looking at his cap, this was effectively the state of the system he assigned to whether he was going to see pink or blue. He had no idea, unless he peeked, but he didn't. So he had no idea. And so it was a 50-50 chance with no interference between the red and blue options, okay? What's bizarre about this is that when you can have a situation where you can know everything you've completely described as best you can within the quantum mechanical constraints of the joint system, it's in a pure state, yet the pieces of it can be noisy. You know, it's a probabilistic, yet you've completely described everything you can about the whole. And that's a very strange property of quantum systems. Right. And more generally, we can say that the amount of entanglement could be measured as the von Neumann entropy, entanglement of a pure state, is the von Neumann entropy of marginals. information theoretic way of defining how much information am I missing in the pieces that I should have had. And the base of the log is up to us. Okay. And as we said, for a pure state, this is the marginals have the same entropy and thus the same von Neumann entropy. Okay. They're the same when we have an overall pure state. Okay, so finally, all of these results come down to what's called the Schmidt decomposition. In the Schmidt decomposition, what we wrote is that if I have a state, a pure state, in the joint Hilbert space of a tensor products Hilbert space, then this state can be written as in the following way. It can be written as this decomposition. Where this chi is called the Schmidt rank, which is less than or equal to the minimum of the two dimensions. That's as big as it can possibly be. These things are positive numbers, which are known as the Schmidt numbers. I mean, I could make them equal to 0 also, but then it wouldn't contribute to the sum. So I could include them if I wanted to. And these guys are called the Schmidt vectors, which are orthogonal and normalized. In their own Hilbert spaces. Okay. So the Schmidt decomposition we're going to prove in a moment, but the Schmidt decomposition is the whole story when you think about bipartite pure states. You want to understand entanglement, you got to understand the Schmidt decomposition. And the marginals are given as such. Also known as the reduced density operator. Where this is the square of the Schmidt numbers. Okay, so the spectrum of the two marginals is the same. They have the same probability distribution, and the U's and V's are the eigenvectors of the density operators. The marginals don't uniquely determine the whole because we don't know about the phase relationships between these guys. Okay. All right, so how are we going to prove the Schmidt decomposition? So let's consider an arbitrary basis. By the way, isn't this just the expansion in a basis? I mean, what's so special about this? I mean, it just looks like I have a basis for A and a basis for B, and I expanded in that basis. Why can't I just do that in that basis? Well, generally, if I have an arbitrary basis, as we remember, there are A times DB dimension things, and this only goes over one index. So importantly, the Schmidt vectors depend on their functions of the state itself. It's not an arbitrary basis. It's a very special basis. It's the basis defined by the Schmidt decomposition. Let's see how that works. So now let's consider an arbitrary basis. That arbitrary basis, for example, is a tensor product. That's an example of some basis, where E sub I and F sub j span the individual Hilbert spaces. So this is a basis with dA times dB elements, okay? And let's expand the state psi for the joint system in the basis, where these gamma ij's are the expansion coefficients. I could think about these expansion coefficients in lots of different ways. I could think about it as a big column vector with dA times dB elements in it. Or I could think about it as a matrix, okay? So I'm going to think about this, for example, as elements of a dA by dB rectangular matrix. Could be square if dA equals dB, but it's just more generally a rectangular matrix, okay? All right, so now the Schmidt decomposition is really all about the singular value decomposition of this matrix. So let's remind ourselves, or tell you something if you've never seen this, about the singular value decomposition. And to do that, I like to think about this. So this is a piece of linear algebra. Let's say I'm going to think about this. I like to think about this abstractly in terms of operators rather than just a bunch of matrix manipulation, okay? Because I find it clearer to understand what's going on, okay? So let's say that I have, let's just start with what we know best. Let's think about Hermitian operators. Let's say A, that is a linear operator that maps a Hilbert space onto itself, okay? What we know about the system is that A can be written as, in a spectral decomposition, we could diagonalize this matrix over, I'll just call it A sub n, or A sub I, where I goes from 1 to the dimension of the Hilbert space, okay? Some of them could be 0, if I like. And if I were to write A in a basis, then these matrix elements, let me call these just for the heck of it so we can, let's call it mu. That'll label our eigenvalues. Then I can diagonalize this matrix through a similarity transformation, which is really just a representation of the eigenvectors in the old basis, right? So if I were to write Aij, that is E sub I, A, E sub j, that is equal to sum over mu V, A mu, E I, A mu, A mu, E j, right? I can never do these things right unless I do an indirect notation. Which I can write as sum over mu and mu prime, EI, A mu, D, mu prime, A mu prime, EJ, where D mu prime is a diagonal matrix with the eigenvalues on the diagonal, right? And I can think about this as these are the elements of a unitary matrix, okay? The columns of a matrix that are the eigenvector with respect to the basis is a norm preserving thing, so that is a unitary matrix, and this is U J U prime star, which is the elements of U dagger U prime J. Okay, so this is familiar to everybody. This is how you diagonalize a matrix, or it's one way to just formally think about that diagonalization of a matrix as I can write the matrix as a similarity transformation on a diagonal matrix. I can invert this and diagonalize it, okay? So this is, I can diagonalize. And we also know if it's Hermitian that these guys are real. And that also that the eigenvectors, assuming there are no degeneracies, but I can always find eigenvectors with degeneracies such that these guys are orthogonal, right? Things we should all know from linear algebra, and we've done it a million times in quantum mechanics, right? Okay, so the singular value decomposition is a generalization of diagonalization for rectangular matrices, arbitrary matrices. So here's how I like to think about it. Let me get my notation right. Okay, good. So let me define a linear operator which has as its matrix elements gamma ij. They could come from wherever. EIA outer product FJB. Okay. Now this operator maps the Hilbert space B into the Hilbert space A. Okay. I can also think about the adjoint operator as mapping A to B. Okay. So this is an operator that doesn't take vectors into the same Hilbert space if the two subsystems are not the same Hilbert space. It's a more general construction. Okay. Now, what the singular value decomposition tells me is that I can write this operator in the following way. In a kind of bi-orthogonal manner, with left and right eigenvectors, sort of. Okay? So D less than here is the minimum of dA and dB. Some of these might be 0. These guys are going to be greater than or equal to 0. Okay. So what does this say? It says that this operator, if it acts on the state u sub mu on A, gives me the eigenvalue lambda back. No, the other way around. Because it acts on V. So it acts on V on B, it gives me the eigenvalue U on A, right? So it's not really an eigenvector in the same way that this we had for a Hermitian operator, but it's a bi-orthogonal set. Similarly, if I act this with U on the adjoint, I get lambda mu V mu on B. You with me? So, and these guys are bi-orthogonal. That's to say, this is orthogonal to itself, and the V's are orthogonal to themselves. So how do we prove that I can do this? The way to do it is to look at the square of the matrix. So let's look at this matrix. Okay. This matrix is Hermitian. What's the dimension of this matrix in this case? This guy is a dB by dB matrix. Right? This guy is also Hermitian. This is a dA by dA matrix. Therefore, I can diagonalize both of these matrices, right? And moreover, this is not only a Hermitian, this is also a positive matrix. So is this a positive matrix, which means that its eigenvalues are positive. And those eigenvalues of these two matrices are in fact the same. You can check that for yourself because they have to, this is where they came from, okay? So they have, these two matrices have positive eigenvalues that are at most D less than non-zero values. Because this guy, say dA is less than dB, if I have to have the same eigenvalues in both cases, such that they came from this original matrix, then the most I can possibly be is whatever the smallest matrix is. If they're positive numbers, I can take their square roots. And their square roots are this. So we can call the eigenvalues of this, the eigenvalues of this or this are the squares of this, and the square roots of these guys are called the singular values of the matrix. Okay, so the singular values are the eigenvalues of the matrix times its dagger in either direction. Okay, now question for you. Suppose that gamma happened to be a Hermitian matrix. Are the singular values the same thing as the eigenvalues of the matrix? Because I could have diagonalized it. That's right. So it's not exactly, they're the absolute values of those guys. So when there's something special, something different here, because now I have to ask about these these u's and v's. What are they? Well, they have to be defined relative to one another such that they came from this overall matrix. Remember, what are the v's? Well, they are the eigenvalues, so the v mu b's are the eigenvectors of this. And the v mu are the eigenvectors of that. Okay. Now, of course, if dA is not equal to dB, I'm going to have more of one of these than the other. However, some of them will certainly be associated with zero eigenvalues, and they don't contribute in any way to the representation of the matrix. By the way, the number of non-singular values is the rank of the matrix, okay, which is what comes in there. So we can finally look at the relationship of how I get from the matrix gamma ij to the singular value decomposition in the same way that I did the unitary transformation for the Hermitian operator. So gamma ij is let's see, how do I write this? Right, good, I was doing the right thing. It's that matrix, right? Now, if I say that I want to relate that to the singular value decomposition, I plug that in. And again, I'm going to write this in terms of a set of unitary matrices and a diagonal matrix. Where my diagonal matrix is the matrix with the singular values on the diagonal. Yes?
So, wait, what is the relationship between eigenvalues and singular values?
Well, for this matrix, this general rectangular matrix, doesn't generally, the singular values are the square roots of the eigenvalues of this matrix, which are the same as that. So the singular values are the square roots of those eigenvalues. But if I had, if gamma were a Hermitian matrix, and I wanted to ask what is a singular value decomposition, it's not the same thing as a spectral decomposition, because the singular values are the eigenvalues of the square of the matrix. And those are the singular values, the eigenvalues of the square of the matrix are positive numbers you lost, whether they're positive or negative. And so the singular values of a Hermitian matrix are the absolute values of the eigenvalues, okay? Which means that whether it's positive or negative is buried in a particular phase convention that you have to put in for the singular values, okay? Now you would never write the singular value decomposition of a Hermitian matrix. You would just diagonalize it and keep the phase, otherwise it gets too complicated.
Interesting.
Right, yeah, go on.
There's another question.
Yeah.
Is finding SVD harder than spectral decomposition?
No, I mean, at the end of the day, you're just
Looks like it.
diagonalizing
Okay.
a matrix. Yeah. You're diagonalizing two matrices rather than one, right?
Yeah.
Because you gotta find the U's and the V's, right? So this guy we said is a unitary matrix, and this guy is also a unitary matrix, but a different one. Okay. And this doesn't work. This guy is supposed to. Anyway, right. So once I have that, I have the Schmidt decomposition. This is a dA by dA matrix. This is a dA by dB matrix with diagonals with only the smaller one, and this is a dB by dB matrix. And that's a dA by dB. So now with all of that said, we can put it together and put this into the singular value decomposition of this matrix into the sum. Let's do it. The sum over I and j, I'm not going to put the limits of the integration in. The sum over mu. Now I only have one index, this is diagonal. U I mu, lambda mu, v dagger mu j. Okay, where this we said was equal to ei u mu, and this was equal to v mu fj. This is in subsystem A, this is in subsystem B. And then I need the kets, thank you, Cole. But let me do this, because I'll put one ket there and put another ket there. For B.
Second
Blah, 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 blah. Right, so now this I can write as that. I just plugged in the star of that. Okay? And now I can sum over I and I can sum over J, and what I get is just the sum over mu, lambda mu, sum over I, that's complete. Sum over J, I get V mu star. Now, that's not quite what I wrote here because of the way that I defined the singular value decomposition in terms of the outer product rather than the tensor product. It's a detail. Don't worry about it. You never do this. But the point is, as you'll see in Nielsen and Chuang, he writes this as the transpose, not Nielsen and Chuang, it's not he, it's they. Although I know Mike better than I know Ike. Because of this reason. It's a technical detail. But the point really is this, that the Schmidt decomposition is really just the singular value decomposition of the expansion coefficients. And with that, we could find in principle, with all the right phases, what the Schmidt vectors are and what the singular values are. Okay, yeah?
Does Isaac really go by Ike?
Ike Chuang, yeah.
Oh, okay.
Yeah. Michael Nielsen does not go by Mike, though.
Oh.
He goes by Michael. But
Thank you.
Ike Chuang is Ike. Yeah, I don't think I've ever heard of Isaac. You've ever used it. Yeah.
Okay.
You know, they met here in New Mexico. Ike was a postdoc at Los Alamos when Ike Chuang was when Mike Nielsen was a student. Mike Nielsen started at the same time I became a professor at UNM, so we're all right. What am I saying? Right, very good. So that's the Schmidt decomposition and something we'll get some practice with. Again, I just want to emphasize it's an interesting fact that this, you know, the kind of a way, how much entanglement you can get depends on the dimensions of the subsystems. Because the biggest this can be, which tells me how many different sort of orthogonal pairs I can superpose, is the minimum of these two things. So for example, if one of the systems is a qubit, the most entanglement I can ever get is one entanglement bit, one E-bit, as it's sometimes called. Even if this guy is infinite dimensional. And that's a problem we'll look at in homework. For example, the Jaynes-Cummings model. In the Jaynes-Cummings model, we have the entanglement between a two-level system and a harmonic oscillator. But I can totally describe that by two Schmidt vectors. Interesting problem. Let's study that in homework. All right, excellent. All right, so what I want to talk about now is this point that I'm just kind of erasing about how different the singlet is from other correlators. Of course, the whole story of EPR and Bell's inequalities, and I want to quickly review that. Let's see how quick I am. Oh, rejected it.
You should have pretended you made it for the recording.
The recording would know better.
I guess the rest.
Something I expect everyone has seen, but I want to say it's again, because we're going to see there's a very important relationship between this story and the story of quantum optics. In some sense, you know, part of quantum optics was born as a way of trying to really put these ideas to the test long after they were especially when EPR was, you know, first, the first paper was written in the 1930s. So, you know, Einstein, Podolsky, Rosen, in 1934, tried to show quantum mechanics is incomplete. And the argument is so beautiful and simple, it's worth repeating it. So the idea, what EPR considered, said, hey, look, let's consider 2 degrees of freedom. Described by, say, A and B, each one described by some position and some momentum, which have observables X and P associated with them. Okay. And let's consider the relative position and the center of mass momentum. Okay. These guys commute. So I can imagine a scenario in which I do a measurement where I can have a definite outcome, something that can simultaneously be an eigenstate of both of these guys. So they consider the state which is an eigenstate simultaneously of these 2 things. That seems perfectly legit, to the degree to which we can ever really think about things that are eigenstates of position momentum. They don't really exist anyway, but we can get as close as we want as possible to these being good eigenstates, okay? In particular, we can think about something that's just, for simplicity, let's just take those eigenvalues to be 0, okay? You could certainly consider such a case.
Shouldn't the state be labeled EPR?
It should. Thank you. So if that's the case, then if we have these 2 parties, always affectionately known at these days as Alice and Bob, who can measure these things, then what this tells me is that if Alice finds her particle at XA, then she can predict with certainty will find his particle at x speed, because the difference in them is certainly 0. Um, right? If you care to look. And similarly, if Alice measures the momentum of her particle and finds PA, then with certainty she knows Bob would find momentum PB equals minus PA if he cared to look. Okay. And that was like the experiment that Brandon and I did. At least for that one thing we did, which was looking at the color, he knows for sure what I'm going to find because there was a particular correlation between them. But the fact that he could predict what I was going to see, and the fact that, so let me just write this one other important idea that came out of EPR, which is the notion of an element of reality, which is to say, if Alice can predict with certainty the measurement outcome of Bob, and if she is space-like separated from Bob, as Bob is outside Alice's light cone. So there's no signal in any possible way, according to the laws of physics, that Alice could have sent a message to Bob. Then there existed an element of reality associated with Bob's outcome. Let's try to unpack that. It's worth just thinking about what that means. When Brandon and I did the experiment, he predicted that my cap was blue. He could predict that with certainty because of the correlations that pre-existed between those two caps. But the cap, if he could do that with certainty, and what he does in no way affects my measurement, because he's outside my light cone, well, he wasn't, but let's pretend I was, then have always had that color. It was that. I just didn't know it, and when I looked at it, I saw it was blue, but it existed. The measurement didn't cause that color to come into existence. There was an element of reality time before that. And so the notion of incompleteness of quantum mechanics is thus to say what the argument of EPR is, and to say, since Alice can predict Bob's X outcome with certainty, Bob's X is an element of reality. And similarly, since she can predict his P sub B, then his P sub B is an element of reality. Implies both XB and PB are elements of reality, and both have definite values. But quantum mechanics says not possible to have a definite value of both position and momentum. Seems pretty logical. Yeah.
So the quote shows up, I think, is it Schrodinger, unperformed measurements have no outcomes. Like, you can't do both of those simultaneously.
Right. Well, that it is Bohr who says.
Oh, is that
who said
Bohr?
that.
Okay.
So Bohr argued back and said, no, because the Copenhagen idea is that there are no outcomes until you do the measurement, and EPR says, but I don't care about that philosophical point. This is just clearly, if I can predict your value without in any way affecting it, then that value had to have been there, because how else, so it's a perfectly logical argument. What you're saying is, of course, the bizarreness of quantum mechanics. I mean, we can measure X and P at the same time. I already talked about that. I stamped my foot over and over again. But that's not the same thing as measuring X and P definitely. If I do that joint measurement as a heterodyne measurement, those are going to have different kinds of measurement outcomes. But, this sat there for 30x years because of this question. Well, is this just a philosophical thing? Now, I want to just, one point I realize now that I hadn't said in our overall review of entanglement, is that what we mean as entangled depends on the subsystem decomposition. But not the local basis. What do I mean by that? So what we just said, if I have a Schmidt decomposition, which I can always write down, I can, in principle, if I look at a local unitaries, as I say, I rotate bases locally. This is just a new set of vectors. I can always do that. The entanglement is unchanged, right? Because the entanglement is determined only by the singular values. So this has the same entanglement as the original state. However, let me think about the following situation that is somewhat related to the EPR state. Let's say I have two particles on a line. Or they don't have to be on a line, they could just be two particles moving in three-dimensional space. And I can think about particle A and particle B, which has its own position momentum. So I could write the Hilbert space of this decision as the motion of particle A or the motion of particle B, right? However, I could also write this as a tensor product of the relative motion and the center of mass motion of the two particles. And I can have a situation, for example, you think about the hydrogen atom. If I thought about the Hamiltonian for this system, I have the center of mass, the kinetic energy of the electron and the proton, and the Coulomb energy associated with the relative position of the electron and proton. That Hamiltonian is not separable. This does not equal the Hamiltonian of the electron plus the Hamiltonian of the proton because of the interaction term. Remember, the notion of separability of the Hamiltonian is if the Hamiltonian is a sum, whereas the separability of the unitaries is the product. So this Hamiltonian, though, is separable in terms of relative coordinate and the center of mass. Which means the eigenstates of the Hamiltonian are separable in relative and center of mass coordinates, but the electron and the proton are entangled with one another. Their motion is entangled. So I just wanted to emphasize this fact because the EPR state is a state that is separable in relative and center of mass coordinates, but it's entangled between the two particles. Okay? And we're going to see, well, so what is the EPR state? It's not a normalizable state, but it's a state we can think about in principle. I can think about it in the position basis. The position basis has XA tensor XB. That's the position basis for the two particles. But in this case, what I have is that the two guys have the same position because their relative distance is the same. Or I can write this in the momentum basis. They have their relative momentum. The center of mass momentum, yes. It's 0. That's the EPR state. Notice, as written, this is a Schmidt decomposition. These are the Schmidt vectors, but it's over a continuous variable. It has an infinite, it's not a normalizable state. However, I can think about this. This is actually, as we're going to see, this is the limit of a two-mode squeeze state. That's to say, I can think about, in the same way that I think about position eigenstates, as the limit of infinite squeezing. So I take X and P, and I have, this is a squeezed state. If I squeeze this infinite, 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 I'll get a position eigenstate. The EPR state has squeezing in the relative coordinate, say, of X, and anti-squeezing in P, but squeezing in the center of mass of P, and anti-squeezing. We'll get to this, okay? So it's an interesting relationship to quantum optics from the original EPR state. But one thing I want to mention, interestingly, and you'll see this in your homework, you know you love it when I say that, is that the EPR state is classical in the following sense. Its Wigner function is positive. Implies there exists a local hidden variable model. That describes the EPR thought experiment. Actually, Bell knew that right away, which is why in the original paper he didn't use the EPR state. But just to conclude, let's just say a few words about what we mean by a local hidden variable model. So John Bell, 30 years later, I think 1964, something like that, a couple of years apart, revisited EPR and said, is there something other than Bohr's, pronunciations that you're just not allowed to do that, so don't bother me, Einstein. That is testable, that would distinguish what EPR were saying about the existence of elements of reality compared to what happens in technology. Is there something more than you just can't do that, so I said so. It's just the way it is. And this is the brilliance of John Bell, to put that to the test. And so he introduced the idea of what's called local hidden variables. Now, local hidden variables, I just want to say, this is exactly what one might expect, that there's something, yes, there are random outcomes, but they're random just because we don't have complete information. If we can complete the information, then we would know the outcome, but there's something there that tells me what the outcome's going to be. I just don't know it. And the whole idea about local hidden variables is about the question of if she can predict the outcome with certainty and he's outside the light cone, the fact that she can't affect his outcome is what we mean by local. So the locality is about the fact that the measurement Alice does can in no way affect the outcome Bob sees. Okay. So whether Alice chose to measure position or momentum on her particle in no way affects the outcome Bob is going to see. So what that meant is that those local hidden variables is that there is a hidden variable. We'll call it what Bell called it was lambda. We don't have complete information. So there's some probability distribution of lambda. There's something that would tell us what the value of lambda is if we can look for it, but we don't have that information, so we assign a probability to it. The fact that it's a local hidden variable means that the measurement outcome that Alice sees depends on lambda, but we don't have lambda, and her measurement setting. What she chooses to measure. Bob's measurement outcome depends on the same hidden variable and his measurement setting. But what makes this local is that Bob's measurement outcome has nothing to do with the measurement setting Alice chose. And Bob's measurement outcome has nothing to do with Alice's measurement setting. Yeah.
So lambda is the local hidden variable?
That's right.
How is it the same for A and B?
Well, just
if they're
here's a
far
local
away.
hidden variable. What pen did I give?
Oh, I see.
We share that hidden variable. Our outcomes are correlated. This is always confusing.
Yeah.
There's something that correlates their measurement.
In the
It's not
first
that
place.
lambda is local to them.
Mhm.
They have to have some point be local to that we did this,
Mhm.
but then we share that random variable. And in the EPR case, what it would mean is the following. I'm going to send out two particles that are separated by some, let's say instead of, that relative distance is x naught, just to make this go. Okay. I'm going to send out two particles that are separated by x naught, such that this guy is always moving with opposite direction to that. I'm not going to send you the center of mass that I'm going to send you is going to be completely random. That measurement, that's a completely classical distribution of possible positions of momenta, which are correlated in a very particular way, such that their separation is always x naught and their relative momentum, and their center of mass is completely uncertain, and their center of mass position is completely certain, and their relative momentum is completely uncertain.
Yes.
That would give me exactly the EPR, and it would be associated with elements of reality. Okay, well, I couldn't get there exactly, but I could get damn close. So, interestingly, the EPR state is describable in that way, interestingly. But the notion of the local hidden variable isn't that the local hidden variable is local to A and B, it's that the measurement setting, that what Alice sees depends on local and what she chooses to measure, but Bob's measurement, what he chooses to measure, doesn't affect her. That's the locality. And the genius of John Bell was to show if you made this assumption, then there are measurements, there are experiments you can do which show that quantum mechanics can't be described this way. How can that be? Yeah, we'll review that next week. All right. I'm gonna have to take some photos of me doing it, and then we'll splash.